This presentation goes over our method for optimizing for focus-dependent camera parameters. To model a scene, we must know the camera system's intrinsic matrix and distortion parameters, which model how scenes in camera space are projected to the sensor. To do this, we can take many photos of a checkerboard pattern and fit a camera model to the photos. However, standard camera calibration doesn't take into account that a camera's focal length often also changes with focus distance. This means that one single camera model can't accurately represent the camera's true behavior. To remedy this, we must calibrate the camera at many focus distances. One way we can calibrate for the change in focal length is by taking many images of a calibration checkerboard at different distances. While this does work, it consumes large amounts of both capture and compute time, which could be better spent. So, we present a faster calibration strategy. We take an initial camera calibration as usual, then take a set of images with the same pose but different focus distances, a focus stack of our own calibration pattern. Using this focus stack, we optimize the camera's parameters for each focus distance. The optimization process is accomplished using Mitsuba, a differentiable rendering engine. Using the derivatives provided by Mitsuba, we apply gradient descent to optimize for a camera matrix which most closely reconstructs the image captured by a camera for a given depth. Comparing the results of our optimization to the baseline estimated parameters from brute force calibration with checkerboards at different depths, we observe that our model does well for all tested patterns at mid-ranges, but performance falls off for some patterns at close and far ranges. This indicates that optimization stability is highly dependent on calibration pattern. We identified 3 of our patterns which best follow the baseline. Comparing these best performers to our worst performers shows that the optimization does significantly better on patterns with dots than with hoops. It also struggles with densely packed elements. We believe this poor performance is due to an increase in hole count increasing the number of local minima when optimizing. To show the practical use of our model, we evaluated its performance for sparse 3D scene reconstruction. We compared the reprojection error when using a single camera model for all depths with our depth-varying camera models. While our model did achieve a reconstruction error lower than the baseline on all tests, the margin is extremely small, making the results inconclusive. Comparing the outputs on dense reconstruction also yields similarly inconclusive results, with all reconstructions appearing nearly identical. Additionally, our model has some limitations. To simplify our model, we assumed constant distortion. However, if this assumption is not valid, it may throw off our results. We also only use a single pose of our calibration pattern, which may cause the optimized parameters to be noisy. Some potential avenues for further research are to use multiple pattern poses to increase stability, applying our model to more lenses and lens types to further prove our model, and applying more robust validation methods to increase certainty in our results. In conclusion, we presented a method for calibrating a camera at multiple depths using a focus stack of a custom calibration pattern. Thank you for watching.